I'm with Shanbhogue. I'm a architect, work for Rivos. Uh, I work actively with the RISC V International to develop standards for specifically targeted for the server space. And today I'm going to talk about what we've been working on to standardize server SoC specification. So for people who are familiar with the ARM ecosystem, this is a similar kind of effort as the server-based system architecture. So um, just to lay some background, when I bring up the term, I want to just briefly define the term server. So when we say server, we conjure up images of beefy compute system, and so it's typically a computing system that manages or distributes resources, services, and data to other computers or devices, typically over a network. So it serves information and resources upon request. And some typical characteristics of a server are that they are expected to operate continually. They have typically a high bar on requirements such as reliability, availability, and serviceability, security, performance, and quality of service. So these are some of the vectors that we try to focus on as part of the server SoC standardization effort, and this is sort of the culmination of a set of efforts that went on over the last couple of years in order to create the specifications for some of these capabilities, such as the security capabilities like the IOMMU or the RAS, standardizing the RAS infrastructure for RISC-V, standardizing the quality of service infrastructure for RISC-V, and so on. So as I go through the next few set of slides, I'll also briefly touch upon those efforts. So to start with, let me say what was the goal that we intended. What was the goal for this standardization effort? The key goal is to enable operating system and hypervisor vendors to support server SoCs built with the RISC-V processors with a single binary OS image distribution model. As my some of my colleagues who spoke before me talked about how distros want to deliver one image. They don't want to be creating distributions per SoC, per platform. And our goal here was to standardize the requirements for the hardware interfaces and capabilities provided by server SoCs to software. Uh, and we focused on a set of standard capabilities where there's typically no need for innovation or novelty because there doesn't exist any, and divergence is unnecessary. And so these are sort of infrastructural capabilities where, while there may be slightly different ways somebody might do it, but it is not necessary to do it for the purposes of, innovation or novelty. And the success for us is when distros like Red Hat can say, here's an image, and it works across various implementations of RISC-V servers as long as they comply to the server SoC specification. I would also call out that this specification is also part of a broader set of specification that we're putting together. So for that reason, I would like to draw attention to what we're also working on, standardizing a RISC-V server platform. So when I say a server platform, it's a collection of specifications, and in this collection of specifications, the server SoC is the one key ingredient, and we'll talk a lot about that. But in addition to the server SoC specification, we're also building a specification for boot and runtime services. So the boot and runtime services encompass recipes for the boot and runtime using UEFI and ACPI and SBI. And so it provides this standardized interface for operating systems and hypervisors to interact with the server SoC through the abstractions of UEFI and ACPI. The other set of capabilities involve a security model. So building a security guide, so to say, which defines the rules for common security infrastructure capabilities such as debug authorization, secure boot, firmware updates, firmware resilience, and other use cases such as confidential computing. It complements the server SoC spec and the boot and runtime specs, and provides the recipes for implementing security capabilities into this mode. And lastly, managing such platforms is very important. So again, we want to use open standards for platform management and provisioning, and build upon the work done in forums like DMTF and OCP, and adopt these open standards for the RISC V server platform. So focusing on the server SoC specification itself, this is sort of an outline of the various rules that the specification includes. It talks about capabilities such as clocks, timers, and interrupt controllers, rules for integrating an IO-MMU into the SoC, rules for integrating the PCIe subsystem into the SoC. Reliability, availability, and serviceability guidelines, QoS guidelines, manageability, platform monitoring, and security. So it's a lot to present, but I'll try to give an overview of what the specification contains as far as each of these buckets of rules are concerned. The first set of rules that the specification lays out are around clocks, timers, and interrupt controllers. So it standardizes, for instance, the unit of time as observed by the application processor as having a granularity of a resolution of a nanosecond. And this is important because we want the view of time to be standardized such that applications and operating systems can rely on this unit. And also as far as capabilities such as VM migration go, having time unit of time being different on different servers is not very conducive to support things like VM migration. The second thing the SoC specification standardizes on is the interrupt architecture. So it requires the RISC V advanced interrupt architecture, or AIA, to be supported, and requires delivery of interrupts as message signaled interrupts to the heart. As most of you must be familiar, MSI is sort of the native interrupt mechanism for standards such as PCIe, which are critical IO standards for servers. And so standardizing around the AIA architecture provides the least friction and the most natural interrupt architecture for these SoCs. Now, it does not preclude the use of wired interrupts. So there might be a few wired interrupt sources in the SoC, but it does require the use of an APLIC to convert those wired interrupts to message signaled interrupts as far as the application processor concerned. The other things that this specification tries to standardize on are things like the number of VS mode interfiles that must be supported. So this is again providing some semblance of minimum expectations that an hypervisor can have as far as the number of virtual CPUs it can support on a hard and so on. And also things like the minimum number of interrupt identities that an operating system can expect to find an interrupt controller implementation on such SoCs. Uh, the second broad bucket of capabilities that the specification standardizes on is the RISC-V IMMU. So this is a the RISC-V IMMU, lack of an IMMU standard was one of the hindrances to building server SoCs for RISC-V, and about year ago, we got a very capable IMMU specification standardized, and is being quite widely adopted across the RISC-V ecosystem. And the IMMU specification includes support for all virtual address mode supported by RISC-V, as well as support for capabilities such as address translation services, page request services, and a set of security capabilities. So primarily an IMMU is needed in such an SoC to provide capabilities such as memory protection, virtual address translation, virtual address space sharing between devices and CPUs. This is the capability by which the software on a hard can say provide a pointer to a virtual a virtual memory pointer to a device, and have the device and the host operate in the same address space. This becoming increasingly important for use cases involving user space work submission and heterogeneous computing using CPUs and GPUs. Interrupt remapping and virtualization, all core capabilities needed for server platforms to support virtualization. So the specification supports the ability to directly deliver interrupts to virtual machines, bypassing the need to emulate such interrupt delivery through the hypervisor. The specification further requires that all DMA-capable peripherals, be they root complex integrated endpoints, non-PCIe integrated devices, PCIe root ports, to be all governed by a RISC-V IMMU. And it provides rules and guidelines on the minimum device ID and passive bits that such an IMMU needs to support. Requires the support of PCIe address translation services, support for a hardware performance monitor, and various rules for integrating an IMMU into the host bridge, such as doing memory protection checks, checking memory attributes, interpretations of IDs and transactions, and so on. So a lot of these are common sense rules, but having a defined set of rules ensures that the integrators can provide a a predictable experience to operating systems. The next set of capabilities the specification standardizes on are the PCIe subsystem. So when I say PCIe subsystem, this includes the root complex, which effectively is a collection of the root ports, the root complex event collectors, and root complex integrated endpoints. Typically, the root complex uses a host bridge to connect to the CPU and the system memory in the SoC through the SoC interconnect. And It may include one or more IMMUs to provide address translation and protection. And the root complex may itself include integrated endpoints. The specification allows two models of integrating endpoints, either as RCIPs, which are root complex integrated endpoints, or as shown in the endpoint 4 in this example, a endpoint that's connected to a root port, but where both the root port and the endpoint are all on chip within the root complex itself. And of course, it supports endpoints that are off chip, as shown by the endpoint 1, 2, and 3 in this example. So when it comes to the PCI subsystem integration, again, the what we didn't want to repeat the rules provided by PCI SIG as far as the PCI rules are concerned. They are very well documented. But what the specification does, where there are optionalities in those specifications, the specification creates mandates. It also provides rules for integration of PCI into an SoC, such as rules for routing, accesses to PCI configuration space, registers, and handling of completions. So, for instance, it requires support for the RRS handling. It provides rules around how to classify transactions as being type 0 or type 1 transactions, how to treat errors, dealing with the unaligned accesses, and the minimum supported access widths. It's again drawing upon the collective experience of the member companies in the various integration issues that we've seen or in their experience, and trying to warn against do this, do not do this, because if you violate these rules, it becomes a extremely hard challenge for operating systems to work around those violations. It also provides rules for capabilities such as mapping and routing of memory mapped IO register accesses. So it defines things like the requirements on access widths, alignments, and so on. And also dealing with peer-to-peer transfers between root complexes, as well as routing of completions, be it through integrating a switch into the root complex, or by doing what PCI calls as taking ownership, where the root complex sort of terminates the transaction and then reoriginates it at the peer port. Right? There's a set of ordering rules that are extremely important, that they are integrated right, because any violation of the ordering rules can have undesired performance or undesired functional effects when it comes to drivers and applications that rely on the PCI ordering rules for reads, writes, atomics, and so on. We also provide rules around dealing with the coherence and cacheability. For instance, this specification requires that that all all IO transactions must be IO coherent, right? So, and that simplifies the type of management that software will need to do compared to having non-coherent IO devices, which would require extensive management of caches through things like flushing caches and invalidating caches and so on. Error handling is extremely important for this class of platforms. So it mandates and standardizes around implementing PCIe error handling capabilities, such as the advanced error reporting and error containment mechanisms, such as downstream port containment, and logging of errors through root complex event collectors, and systematized mapping of root complex integrated endpoints to the event collectors, so that the operating system can, in a rule-based manner, associate RCIPs with RGEX. Security is another important consideration. So it mandates rules for access control services, such as requiring the ACS for source validation and translation blocking to be implemented by the root complex. There are certain optional capabilities that it provides. For instance, servers such as media servers care about time synchronization a lot, and precision time measurement is an important capability for establishing a master time and synchronizing time as seen by devices versus the host. So again, the specification provides rules around resolution of the master time and software access to the PTM master time. RAS again is extremely important. So again, the reliability, as you all know, is a probability that the system continues to provide correct service, right? So and availability is a measure of tolerance of errors, and serviceability being the time to restore service to the correct operation. And among these, the amount of reliability or availability that a server needs to provide is a lot of times dependent on the segment that the server is targeting, with the main goal being to minimize the amount of silent data corruptions and detected and uncorrected errors that can be observed in that SoC. For instance, it is typical for such SoCs to target, for instance, to have goals like not more than 100 silent data corruption fit, or not more than 800 DU fit, right? So effectively, these systems are expected to provide continual service, and even though one fit translates to one error in a billion hours of operation, when you put thousands of these servers together in a data center, those even with an 800 fit target, once you put something like 4,000 SoCs in a data center, you might experience, say, a failure every 4 or 5 months. And I can't emphasize enough how much RAS has been being important, especially for accelerated computing. We've seen, for instance, papers from vendors such as Meta, who expect these servers to be used for things like AI training that runs for months, and a failure is a hugely disruptive event, and they want to avoid failures as far as possible. How does RISC V play into this space? A lot of these capabilities, such as defects per million, failure in time, you address them through microarchitectural capabilities, such as implementing error detection and correction mechanisms for your caches, system memory, interconnects, periodically scrubbing these memories for errors, and through error containment techniques such as data poisoning and the rules for handling data poisoning. So this is where the server SoC cannot provide mandates, but it can provide guidelines. It does that. What it also requires is integrating the RISC V RAS error record register interface, or RERI specification. And what RERI provides is a standardized interface for reporting errors, including their location, their nature, their severity, to RAS handlers in the platform. So this goes into that serviceability space. And the RISC-V RAS ERI, the ready specification, is something that was ratified earlier this year, and is a good addition to the group of specifications that are important to build server SoCs. Um, Quality of service is again an important aspect for server SoCs. These server SoCs are characterized by having large core counts. I think some of the SoCs presented here had, say, 80 cores, and it's not uncommon these days to have multiple hundreds of cores in such servers. And these SoCs are built using multiple levels of shared caches, shared interconnects, shared memory controllers, and so on. And when you have this sort of sharing and coupled with a large core count, which sort of naturally tends to wanting to co-locate multiple workloads, which may not be all related. For instance, if you're targeting a cloud compute server, then you might have virtual machines which may not all be from the same source running the same workload, all co-located and running on the same SoC. This leads to a couple of problems. One of them is a noisy neighbor problem, where depending on who is running along with you on the server, you might see interference in the form of unexpected evictions of your data from caches, contention for memory bandwidth, and so on. And your workload's performance may become non-deterministic due to this interference caused by noisy neighbors. Just can't tune your workload to perform in a deterministic manner. One way you could address that is by underutilizing your server, so that you avoid co-locating, say, disparate workloads on the server, but then you are underutilizing your investment, and from a TCO perspective, as well as things like energy efficiency perspective, that's not a good problem to have. So you want your servers to be maximally utilized. So then the problem becomes, how do I co-locate workloads that might be latency critical without compromising on their service level objectives. Um, and among all these various sources of interference, they can sort of be classified into sort of two types of resources that are contended for. One are capacity resources, such as cache capacity and TLB capacity and so on, or their bandwidth resources, such as memory bandwidth or interconnect bandwidth. And so in this space, RISC-V, again, earlier this year, ratified two specifications. One is called the RISC-V Capacity and Bandwidth QoS Register Interface, or CPQRI. It provides a way to configure capacity and bandwidth allocation among these resource controllers, such as memory controllers, caches, TLBs, interconnects. And once you can dedicate capacity or bandwidth to these workloads, you can provide them more determinism and provide a more robust SLA. The second specification that RBI standardized in this space is called the QoS-ID extension, which provides a method to associate an ID with the workload, so that when the workload makes accesses to these shared resources, such as caches and memories, that ID follows along with the request. And these controllers can then use the resource control ID or the monitoring counter ID to determine the configured capacity and bandwidth allocations and enforce those. As far as the server SoC specification, what it does is it provides guidelines on mitigating these performance interference caused due to resource contention. It provides guidelines on integrating the SSQOS ID and the CBQRI specification, for instance, for significant caches, memory controllers, IO menus, and so on. And it provides guidelines on the minimum number of resource control IDs and monitoring counter IDs that an operating system would expect to find on such SoCs. I hinted upon the fact that management of these platforms is challenging, and especially because these machines get densely packed and located in data centers that uh, if you have to go physically access those machines to provision them or configure, reconfigure, manage, restart, then it is an extreme burden on the extreme burden in the form of operating costs for these. So what you want is a standard set of management capabilities by which you can monitor these platforms. For instance, monitoring sensors in these platforms, such as the temperature, power, the fan speeds, and so on. And also to be able to control parameters such as power limits and to gather data such as RAS error records, all of that remotely using standard tools and protocols such as those defined by DMTF, Redfish, the platform level data model, and the MCTP that provides the transport bindings for these protocols. So the server SoC specification again provides guidelines on implementing standard protocols such as MCTP and SPDM for attestation and message encryption for security. And it also provides guidelines on the hardware capabilities that are needed to integrate with both in-band and out-of-band management capabilities, such as providing a PCIe interface that can be connected to the BNC for facilitating things like remote KVM, providing a management network so that you can provision these platforms remotely. It requires the SoC to provide capabilities such as an I2C interface for carrying IPMI, UARTs, so that you can have remote manageability of these platforms. Performance monitoring is an area where the server SoC specification provides guidelines on incorporating hardware performance monitors into structures such as significant caches, interconnects, PCIe root ports. This capability is important for the applications and system integrators to be able to tune their workloads and manage the placement of their workloads, and to collect performance metrics such as bandwidth and latency in order to determine if their workloads are operating to the expected exhibiting the expected behavior, or are there any anomalies. And to that extent, the specification also provides guidelines on performance monitoring in NUMA configurations, so that if you had any errors in your workload placement, or you want to optimize your workload placement by, for instance, affinitizing that workload, and you want to know how sensitive that workload is to, say, the memory latency, you can use the performance monitors to gather that data, and instead of blindly carrying out experiments, which nobody likes to do. So in summary, what the server SoC specification attempts to provide is a robust set of rules and guidelines to control optionality. in implementing specifications, both specifications from RISC V International as well as industry standards. Um, Again, the goal is that we want to enable OSVs to be able to ship a single image distribution that can be installed across servers implemented using built using SoCs from different vendors. And so the capabilities in terms of the hardware and the runtime capabilities that these OSs and hypervisors expect to find are standardized by this specification. As we speak, this specification is on its way to ratification. It's in its final phases of public review. And we're sort of calling on for member companies and the ecosystem is to implement to this specification and support it. Again, we want to make RISC-V servers predictable, rather boring. There shouldn't be too much excitement when commissioning a RISC-V server. So that's the goal of this specification.